Okay. I'm going to talk about memory controllers, but I'll point out that we'll get back to this. I think this is really fascinating. And this also requires an intelligent controller to exploit this sort of retention time profile. There are a lot of issues here. Okay. Okay, so this, I'm not going to talk a lot about memory controllers, but give you a basic overview. But memory controllers are everywhere. I'm going to focus a little bit more on DRAM, but long latency memories have similar characteristics that need to be controlled. This discussion will be on DRAM, but many scheduling and control issues are similar in the design of controllers for other types of memories. Flash memory is a very good example. If we have time, we're going to cover this a bit. But other emerging technologies, phase change memory, STT-MRAM, memristors, whatever you have, they all have characteristics that are relatively similar to DRAM and also different from DRAM to control. So take this discussion from that perspective. And some of these other technologies place different demands, other demands on the controller as well, like wear out. Whenever you actually write to a location, that location wears out, and you can do only some number of writes. Flash memory has significant read disturbance issues, for example. How do you handle those? And flash memory has other characteristics, like you need to you need to erase a block before you write to a particular page. So how do you do that? And how that erase takes very long. How do you schedule those very long latency requests while you're doing reads and writes? That brings out a lot of issues over here. So flash memory is very interesting. As I said, these are similar to DRAM controllers, except they're flash memory specific, and they do much more. Because flash memory is actually a much less reliable technology to begin with. So you need to correct a lot of the errors. You need to do page remapping internally because of this writing issue. Whenever you need to write to something, you need to erase a block, which means that you need to allocate a page in a block, and then you need to erase that block, and you need to write to that page. Which means that it's good to have erased blocks at places so that you can write to them very quickly. How do you do that? So that's handled all in the controller. And sometimes you have some pages that are invalid in some of the blocks because you've written them somewhere else. You moved them somewhere else, if you will. Which means that some of the pages in a block are actually invalid. So if you, I talk about this block page terminology, but in flash memory, you have pages that are 8 to 16 kilobytes and blocks that are 256 kilobytes or so, like 128 pages or so. And because of the technology, the granularity of erasing is at the granularity of a block. And then you can write to a page after you erase it only after that. And this leads to other constraints. Like some pages, some blocks actually has very few valid pages in them. At some point, they become garbage, and you need to collect them. Meaning you need to erase them, schedule them for erasing. You need to do those erases in the background. How do you do that? How do you decide when something should become garbage? Do you do that proactively? There are a lot of issues in the flash controller that we are not going to discuss compared to the memory controllers. But just know that it's much more sophisticated than DRAM. And these controllers actually have a lot of signal processing mechanisms, which we may get to as well. And this is a better picture of this. I should have used that picture maybe. As you can see, there are a bunch of other, there's also DRAM actually. There's also a DRAM controller inside the flash controller because there's a DRAM buffer to manage the mappings and to manage the writes internally. So it's not just the flash controller, but also a DRAM controller inside it. It's fascinating to look at this. And if you're really interested in this picture actually comes from this paper that we recently written. This is the result of about 8-9 years of work that we've done in terms of flash memory error characterization. And this covers those 8-9 years of work, plus other works that have actually gone into error characterization, mitigation, and recovery. But it also has a very good overview of the flash SSD controllers. And we have an archive paper that's superseded this one that was written a few months later than this. Okay, I'm not going to cover flash controllers, but there's work that we're doing in this area, so if people are interested, I'd be happy to talk about this as well. This is a simulator that we released for flash memory, and this is, there are similar issues in flash memory, like long latency. How do you fix the tail latencies in flash memory, and there's a lot more to do in this area. Okay, let's go back to DRAM. So even DRAM is not a single type. DRAM has different types with different interfaces optimized for different purposes. There's commodity, there's low power, There's high bandwidth for graphics initially. There's low latencyy. There's 3D stacked. And you can keep adding to this. So even DRAM has proliferated a lot, especially in recent years. It's not just DDR anymore. It's many, many other types. But underlying microarchitecture is fundamentally the same. The bank structure is fundamentally the same. The commands are fundamentally the same. There's not that much difference in terms of underlying microarchitecture. The signaling interface is different. The analog interface is very different. And that's actually one of the biggest barriers to entry into chip design, perhaps. You need to have this analog interface. Everything else may be open source in the chip, but that analog interface is one of the most difficult parts to get open source, perhaps. A flexible memory controller can support various DRAM types, but the analog interface is the biggest limiter. And this complicates the memory controller. Difficult to support all types and app upgrades, because you may actually design your memory controller for your memory chip for 4 years later, and 4 years later, a better technology comes in. How do you actually adapt to that? Well, it may not work out because first of all, your analog interface doesn't work well with that, or doesn't work at all. Even if your analog interface somehow magically works, your memory controller may not be designed for that particular technology. So there are a lot of issues over here. How to design a very flexible memory controller that could work with all technologies is a good dream. It's not clear if it's a realizable dream at low cost. So this is another example of the proliferation of different DRAM types. This is from a paper that I'm going to cover, the Ramulator paper that we've written a few years ago. As you can see, even at that time, there were a bunch of 3D stacked or 3D stackable technologies like wide I/O, HBM, hybrid memory cube that we're going to talk about. So let's talk about the functions of a DRAM controller. Basically, the first function is you need to ensure correct operation, which means that you need to refresh DRAM and you need to obey the timings. We're going to talk about timings later on. You need to service DRAM requests while obeying the timing constraints. Timing constraints are resource conflicts and minimum delays. These are some examples. And you need to translate, the memory controller needs to translate the request to DRAM command sequences. Because as we said, request comes in, I want to read from this address. You need to turn it into some constraints and generate command sequences from that. Okay. And then you need to buffer and schedule requests for high performance and quality of service. Those are other requirements. You need to do some reordering, row buffer, bank, rank, bus management. How do you do that? Especially in the long term, because at this point, taking this action may be a good idea, but that may not be a good idea for the future, right? If you wait just a little bit before opening this row buffer, maybe you'll get some other request to the row buffer that's already open that you have. Maybe you need to be looking into the future a little bit. It's not clear. So, and also on top of this, manage power consumption and thermals in DRAM. Thermals are an increasingly bigger issue in things like this, where heat has not a lot of place to escape, but power consumption is already a big issue. And this is an area that needs a lot more research, in my opinion, in DRAM. How do you actually fix the power consumption issues? Today, the granularity is very large. You cannot turn on and off things individually. You can manage power modes at some granularity, and things are changing, but we're going to very briefly talk about this. So there are clearly a lot of functions. And this is one example of a DRAM controller. I'm going to not talk about this a lot. This is the signaling interface, the analog interface that I mentioned. And this is very dependent on the DRAM interface, the technology that you have over here. So if you want to have a memory controller that can attach to many different types of DRAM, you need to replicate this, right? Which may not be that easy, as you can see. And this actually consumes a lot of the chip area. And then there's, of course, the RTL part of the controller, which is more logic part that does the arbitration and the bank management. And this is one other example. I mean, there are fundamental choices. You can actually have request buffers dedicated for banks, or you could actually have a shared request buffer across banks. Again, the fundamental dynamic versus static partitioning principles apply here. If you have a lot of requests to a single bank, maybe it's good to have a shared buffer such that you can utilize all of the buffers over here. If you have very good balanced requests across banks, maybe it's not good to have a shared buffer because now you need to do the scheduling across all of that shared buffer. The dynamic versus static partitioning of buffer trade-off also applies here. Okay. So scheduling policies, let's talk about that briefly. So what request to schedule first? The first one is really not a scheduling policy. What is a policy? First come, first serve. You don't do anything. You just request whatever comes to you, right, first. And actually, there were some old controllers that used this in the past. I don't think a lot of controllers are using this at the moment because it doesn't take advantage of this row buffer that we discussed, right? Row buffer is a natural cache in DRAM. As a result, many controllers move to this sort of scheduling policy. And in this case, we're not even talking about writes, reads, and refreshes, right? How do you order them is also important, and that goes into a priority order. But this priority order is if a request goes to a row that's open, prioritize that request over other requests, and all else being equal, prioritize older request over the younger request. So clearly, the goal of this is to maximize row buffer hit rate, to maximize DRAM throughput. This also is good for latency because each of your row hit accesses are lower latency than row conflict accesses. So a lot of the controllers use a variant of this. And as I said, the scheduling is actually done at the command level, right? So you may actually have scheduling at the request level and then the command level also, and have a combination of this. But FRF-CFS is column commands are prioritized over row commands. Assuming you converted all of your requests into some commands at some point, you prioritize the column commands over row commands. Read, write are prioritized over activate, precharge, as you can see. And within each group, older commands are prioritized over younger ones. And this is very simple, right? This doesn't even take into account other information at this point. We're going to talk about some of the other information, but we're not going to go into a whole lot of detail and everything. And I've already reviewed this operation, so hopefully you remember the row hits, row conflicts. Okay. So a request scheduling policy is essentially a prioritization order today. Request or command prioritization order. And prioritization can be based on many different things. I'll just give you some examples. It could be the request age that's taken into account, row buffer hit or miss or conflict status, request type, prefetch, read, or write. Which one do you prioritize? I heard read over here. That may not be good because you have actually what may turn read-write scheduling is also important because you have write-to-read switching penalties, which are at the rank level. If you have too many writes that are in your controller, at some point you'll have to switch to scheduling writes because your write buffers will run out. And you may be draining all of your writes at that point in time. As a result, you may be delaying reads. So it's good to intelligently switch between these two different things, writes and reads. So the unfortunate thing in DRAM is there's these timing constraints. So while you're scheduling writes, you cannot schedule reads at the same time because the bus is shared. You're driving the bus in one direction. You cannot drive it in the other direction at the same time because the banks share the bus. So this is a rank level scheduling constraint. You cannot read from a rank at the same time you're writing into the rank. And that leads to scheduling issues. Prefetch versus read, any guesses? You want read again? That may not be necessarily a good choice also. Actually, we have a paper that looked at this. Which one do you prioritize? It turns out sometimes it's better to prioritize prefetches that are accurate. If you know that prefetches are going to be accurate, and if they actually are hitting in the row buffer that's currently open, it may be better to prioritize them over your reads. So it's actually no fixed prioritization policy works well for all workloads from our results. You want to have an adaptive policy that can adapt itself to the accuracy of the prefetches and the status of the row buffer. So this is, yeah.
No, I was about to say, I say read, it's shorter word. So.
Read shorter what? Well, okay, basically this is not easy. It's very complicated actually. And it's not easy to find, I think, the optimal scheduling policy because it's very dynamic. But it's fun to think about it. And there's more, of course, right? You can imagine more. What about load miss versus store miss, right? It may still be a read request going into the memory controller, but it may be generated by a load or a store. Which one do you prioritize? Or how do you actually prioritize compared to these? There's more. Request criticality, if you can measure that. How important is this request to the core that's requesting it? First of all, how do you understand that? And do you actually put that into the controller? If you know this, maybe you say, okay, controller, give me this thing first. And I think there needs to be more research in this one. And how do you actually define request criticality? Is it the oldest miss in the core? Or is it defined by how many instructions in the core are dependent on it? Because this actually is a measure of how many things it's going to enable into the future. Will it stall the processor, if you can guess that? Okay, interference caused to the other cores, that's another category. which is very different from everything else over here. If I actually get rid of this request very quickly, will it enable some other request that's very latency critical for some other core, right? So this is becoming a mess, as you can see over here. And you can imagine many other things. Today, we're not using a lot of this information, actually. We're using very few bits and pieces, and it's usually a fixed prioritization order, fundamentally because it's a difficult scheduling problem. It's not easy. Okay. So row buffer management policies, yes? What does that mean? The controller itself, or?
Well, yeah. Well, if I first read from an address, then write to an address, then I want it to be.
I see. Yeah. So I think at least most reasonable controllers satisfy that ordering. Yeah, they don't violate, basically, if you're trying to write to so basically the question was, does the DRAM controller guarantee the ordering of the request? If you send a read first and then a write next to the same address, is there a problem? Most controllers handle that in the order they receive the requests. So they don't violate the order.
So, well, then in that case, it kills the performance advantage that you took.
It might, depending on how you do the buffering also, right? So if you actually, if you get a read request to a cache block that's already in the controller, you may supply it directly from the data that you already have in the buffer, right? So you could actually take advantage. If you're actually accessing the same address and somehow it happens to come to you at the same time, you can take advantage of the internal buffering. Okay, so row buffer management policies, we discussed this very briefly because somebody asked a question. But basically, what I described earlier too was kind of like the open row policy. You keep the row open after an access in anticipation that the next access is going to be to the same row in the same bank. If that's the case, that's good. You get a row hit. But next access might need a different row. In this case, you get a row conflict, and you waste the energy. So clearly, this open row anticipates that, open row policy anticipates that you might need the same row. Closed row policy, in the very strict form, whenever you access, do a read to a row, you pre-charge it immediately. That's very strict. That doesn't even take into account whether there is a request outstanding in the request buffer to the same row. So a less strict form of the closed row policy is close the row after an access if no other requests are already in the request buffer to the same row. Makes sense, but of course, if the next access needs a different row, that's good because you already avoided the row conflict. You didn't wait until the next request came and requested that row, the other row. But if the next access needs the same row that you just closed, then you have a problem. You incur an extra activate latency. So again, adaptive policies are usually better. If your predictor is good, you can predict whether or not the next access to the bank will be to the same row and act accordingly, whether or not to close the row.
Why do you emphasize the wasted energy on the open row on the next access might need a different row? It's more of a latency issue than energy.
Next,
you didn't save anything. You didn't lose anything by leave it open.
oh, I see.
So you have to pre-charge it anyway.
Yeah, you did. Yeah, that's right. You have to pre-charge anyway, but you kept the row open. And keeping the row open actually wastes energy, yes. So you did waste some energy, actually, yes. Actually, there's wasted energy because of this also, extra activate latency. I should have put, for parallelism purposes, there should be wasted energy over here as well, yes.
That is more like something
Sure.
otherwise wouldn't do.
Yes, but in this case, I think I emphasize it because you may not think about it, open row wasting energy, but an open row, activated row actually wastes energy. And that's actually a problem in these sort of devices. So some of these devices aggressively close the row after some time. Okay, so this is a simulation of the policy, first access, next access, which I'm not going to cover. You can take a look at it in the slides. Basically, it just said what I said, except it's simulating what is the first access, next access, whatever the commands needed for the next access. Power management, very quickly. Power management is also important, clearly. DRAM chips have power modes. I think this is an area that requires a lot of innovation, actually. Maybe the idea is very simple. When you're not accessing a chip, power it down. So there are different power states. Active is the highest power. Or all banks can be idle. and there's a power down state, and this definition varies depending on the chip, and then self-refresh. This is the lowest power. Basically, there are shades of gray over here. I think there needs to be more work in this area, and if you're interested, I can recommend some papers. But self-refresh is essentially a state where everything is turned off except for the internal refresh circuitry. Okay. But there's a trade-off because when you want to move from self-refresh to active, it takes a long time, on the order of microseconds, if I remember correctly, but this may also depend on the technology. So it takes about microseconds, and you cannot access the chip. So it may not make sense to go into the self-refresh mode if you're going to get out of it quickly. Right. So there are trade-offs here. And the granularity of the management is also important. Do you do it at the bank level? Do you do it at the even or coarser granularity? As your granularity increases, reduces, your memory controller complexity also increases, as you might imagine. But this is something that we're not going to talk about a lot, but keep that in mind. That's also important. That's going to exacerbate the difficulty of DRAM control, only exacerbate it. Okay, so DRAM control is actually not easy. You need to, why are these difficult to design? You need to obey the DRAM timing constraints for correctness, first of all, and there are many timing constraints. Actually, I say 50 plus over here, but it's really 100 plus, maybe 200 plus by now, but 50 plus at least the more interesting ones. As I said, there's, like this is one example, write to read delay. Minimum number of cycles to wait before issuing a read command after a write command is issued. TRC is the, quote unquote, the latency of memory. Basically, this is the minimum number of cycles between the issuing of two activates to the same bank, row cycling delay. If you have bank conflicts, basically, you need to wait for TRC, minimum TRC. And there are many of these. I'm going to cover a bunch more. On top of this, you need to keep track of many resources to prevent the conflicts, and there are many resources, as you can see over here. You need to handle DRAM refresh, and DRAM refresh has some elasticity today. You can actually delay refreshes by some number of cycles to schedule some reads or writes that may be critical. So handling that is important. You need to manage power consumption, and you need to optimize for performance and quality of service and whatever other metric in the presence of all of these constraints. And reordering is not simple. It's not as easy as we just discussed. And fairness and quality of service needs actually complicates the scheduling problem. And remember that picture that I showed you with many different agents, with many different memories, that becomes even more complicated. So there are correctness issues, and there are performance issues, and there are power issues, thermal issues. There's a lot. These are some examples of the timing constraints. This is from a paper that we wrote about 8 years ago. I'm not going to cover this, but this talks about some of the timing constraints. Write recovery, for example. After you do a write, you need to wait for 12 DRAM cycles before you can do anything to that bank. Read to pre-charge delay, activate to activate is the TRC. As you can see, it's about 39 DRAM cycles in this particular technology over here. Okay. And the papers that I recommended actually cover some of these. Actually, maybe I'll cover a couple of these over here. So this is the activation delay. So after you send an activate command, you need to wait for some time for the data to be amplified by the sense amplifiers and to be stable in the sense amplifiers. That's the activate to read delay. That's called TRCD over here. And in this technology, it's 15 nanoseconds. Activate to write delay is the same thing. Basically, you need the data to be stable to be able to write. And then you can send the read request, and then there's a Cksed latency, TCL, read until you get the first data. It's about 15 nanoseconds also, as you can see. And then there's this data burst latency. That's about 7.5 nanoseconds in this technology. So that gives you the activate to data out, the first access latency, as you can see. And if you want to be able to start the next access, there's an activate to pre-charge delay that's also specified. That's called TRAS over here. If I find it over here, it's about 37.5 nanoseconds, as you can see in this technology. And this is the pre-charge delay. There's an additional pre-charge delay. After you issue the pre-charge, the bank needs to be ready for the next activate, and that takes some time to stabilize. That's about, TRP is somewhere over here. It's about 15 nanoseconds also in this technology, right? So as you can see, the TRC delay is the addition of TRAS and TRP, which is about 52.5 nanoseconds in this case. A bank conflict takes about 52.5 nanoseconds. And there are reasons for this, and the reasons are explained in this paper. I like this depiction because none of the data sheets, my Freudian slip comes back, actually talks about this so clearly. in my opinion. Basically, this is the pre-charge state of the array. You activate things. It activates a row. It applies a high voltage over here. The bit lines get connected to the cells over here. The charge in the cell gets shared with the bit line. So you perturb the bit line by just a little amount. And the sense amplifier captures that perturbation and starts sensing and amplifying the data. It basically senses whatever value that you have on these bit lines. So at this point, the sense amplifier knows that, oh, this is 1, this is 0, because this cell over here perturbed this up, and this cell over here perturbed this down. As a result, you got about 0.9 VDD over here and 0.1 VDD over here, and you started with a pre-charge state VDD over 2, which is the middle of the margin that you have, 0 to VDD. So the activate to read delay comes because of the fact that you need to wait until the sense amplifier senses the correct data. It's specified that way. As you can see, if you go over here, the activate to read delay, TRCD, you can find it over here. It's a delay between a row command and a calling command, activate to read or write, and it's at the bank level. Its scope is at the bank level. Its value is this much in DDR3 technology over here. As you can see over here, whenever you actually sense the cell, you destroy the data value over here because the cell capacitor shares the charge with the bit line, and then after that, the value is lost. The sense amplifier senses this, and then it drives the value back into the cell. That's essentially what happens over here. You get a VDD over here, and you get a 0 over here. And at that point, the cell is ready to be pre-charged. So the sense amplifier, once it captures the value, it's ready to be read, but it takes some more time to restore the full value into the cell. And once the cell value is restored by the sense amplifier, you can now pre-charge the array. That's why it takes more time to do that. This is basically the chart sharing operation and the sense amplifier operation. I'm going into the guts of DRAM right now, but it's good to know these things because we're going to try to reduce these latencies later on. These are specified with these latencies so that DRAM chips operate correctly, right? And that's where the activate to pre-charge delay comes from. The sense amplifier restores the value into the cell. And after you get the pre-charge command, as you can see, you need to prepare the bank for the next access. What does that mean? You need to pre-charge the array such that whenever you do the next access, you can perturb the bit lines and sense the value, which means that you need to put the bit lines into the reference voltage, VDD over 2, and that takes some time. Basically, as you can see, this was VDD, this was 0. We're looking at only 2 cells. It's actually 2,000 cells over here or so, whatever the row width is. You basically need to set all of the bit lines, 2,000 bit lines, to VDD over 2, and that takes some time. There's a pre-charge circuitry that does that, and that's about 15 nanoseconds over here. If I find it over here, TRP, where is it? It's a row command to row command delay, as you can see, pre-charge to activate, and the scope is at the bank level. So this paper, this subarray level parallelism paper, actually summarized a lot of these. As you can see, there are a bunch of other delays that are at the channel level. At the channel level, you have read-to-read, write-to-write delays, as you can see, for whatever reason, for similar reasons, actually. And at the rank level, you have the read-to-write and write-to-read delays because the bus actually has different directions. OK, so I'd recommend that you take, this is the recommended paper for DRAM background. And that's exactly why you have so many timing constraints. Well, I think the so many timing constraints come from DRAM operations, certainly, but it also comes from the interface. It's good to know that the interface to the DRAM today is a synchronous interface, right? Basically, the memory controller issues a command, and it knows exactly how long it's going to take. And the DRAM obeys that. That's the characteristic of a synchronous interface. You can design a synchronous interface with many different timing constraints, like this. Or you can design a synchronous interface with a single timing constraint. That's the extreme. You can say, whatever command I have, it's going to take a fixed number of cycles. And that fixed number of cycles is going to be the maximum of all of these. Now, people decide not to do that because that maximum is not good, right? That maximum is about, in this case, assuming these are the only timing constraints, is 50. People said, OK, I don't want to wait 50 cycles. I think this is nanoseconds, 50 nanoseconds for everything. As a result, I'm going to have different timing constraints. Now, this complicates the controller, of course, right? Enforcing a single timing constraint for everything is easy. But enforcing many hundreds of these timing constraints is not easy. The other option is to have an asynchronous interface and basically not do away with all of these timing constraints, but memory controller sends a command or whatever request. Maybe the interface is at a higher level or a function. It basically requests an acknowledgement from DRAM when it's done. Right? Or maybe it can keep sending commands, and if the DRAM cannot handle them, DRAM sends back saying, oh, sorry, I cannot handle them, so I'm going to negative acknowledge you. Right? This is called a NAC. That interface doesn't exist today in the memory controllers that we have. That may be a much more flexible interface, as you can see. Right? This is a very rigid interface. Somebody needs to specify these timing constraints, and DRAM needs to obey it, and memory controller needs to obey it. It's basically everybody designs things separately. Whereas the other interface, asynchronous interface, is perhaps much better. It's more of a handshake protocol. You send a command or send a request, and whenever the DRAM is done, it sends it back. And going forward, that may be a much more flexible interface, but it's not clear if that's going to change. So hybrid memory cube, for example, that we're going to discuss later on, has that sort of interface. It's more packet-based as opposed to these timing constraint-based. And if you actually go to an asynchronous interface now, you can actually specify many things potentially, right? You can say, DRAM, I'm going to ship you this function. If you have the capability, do it. Otherwise, send me a negative acknowledgement. Right? And the DRAM says, OK, I can do it, and I'll let you know when I'm done. Right? So that interface doesn't exist. As a result, we're here.
Who specified? This is the DRAM manufacturer?
So this, the JEDEC. Yeah, all of this interface is specified by this JEDEC, which I don't remember what it stands for, but it's called JEDEC. Basically, it's this huge body that's...
Sort of a committee that...
Exactly, yeah.
It's a standard that exists.
Exactly, yeah. It's a standard that exists and that evolves very, very slowly. OK. OK, so as I said, this is also another picture over here. You can take a look at it. But this is, DRAM controller design is actually becoming even more difficult because of these different requirements over here. Timing constraints are also changing. You may actually be controlling multiple different types of memories with different controllers. Especially if you have hybrid memory, now you need to have different controllers for them. And they need to interact somehow with each other. But also you have this application space or changing significantly with different requirements. And if you don't communicate these to the memory controllers, then you have a problem. For example, if the memory controller doesn't satisfy the frame rate requirements of your GPU, you have a problem. And existing memory controllers have mechanisms to satisfy them, but they may not be necessarily the best mechanisms for overall throughput. And that's true for hardware accelerators also. And we're going to talk about that when we talk about memory controllers, interference, and scheduling. But the controller design is actually becoming much, much more difficult going forward. So I'm going to talk about another dream that we had, again, about 10 years ago. The reality is it's very difficult to optimize all these different constraints while maximizing many different metrics. So we had this dream, again, about 10 years ago. Wouldn't it be nice if the DRAM controller automatically found a good solution? This was before the machine learning hype. Now we have the machine learning hype, but I think solutions like this are very good, very interesting to examine going forward. And we wanted to look at this controller. How do we actually design this controller? Because it's actually really painful as a DRAM designer. If you're a memory controller designer, you would know this very well. I used to work at Microsoft Research, and while I was doing that, Chuck Tacker was designing the DDR3 memory controllers. Who knows about Chuck Tacker here? Okay, you should really look at the Xerox Alto system, for example. He was, these were the precursors of the personal computers, Xerox Alto system. He designed it while he was working at Xerox PARC at that time. But he was a Turing Award winner. He passed away. But he was designing these DDR3 controllers for the B engine, Berkeley emulation engine, which was an FPGA-based system. And he was finding it so painful that he said, this was the worst thing that I've designed in my life, the DRAM controller. And he designed the personal computer before many other people did in the past. Anyway, so that was one of our motivations, not his motivation, but we were also designing things. And we said, OK, this is really painful for a human designer to come up with a really good policy. So we should actually have a better mechanism. And this is the idea that we developed. And I think this has a lot of potential going forward in many different system components. But it needs to be done very, very carefully. So the problem is DRAM controllers are difficult to design, which means that it's difficult for human designers to design a policy that can adapt itself very well to different workloads and different system conditions. And workloads change, system conditions change. If you have a scheduling policy like what we described, row hit first, oldest first, That's actually, even if the workloads don't change and system conditions don't change, that may not be a good policy to begin with. So our idea was to design a memory controller that adapts its scheduling policy decisions to workload behavior and system conditions using machine learning. Of course, machine learning is a black box. This is the hype today. The key question is, what kind of machine learning, right? Our observation was reinforcement learning actually maps nicely to memory control. And reinforcement learning is very fundamental. Does anybody know about reinforcement learning? I assume people have taken psychology. Ivan Pavlov, Pavlov's dogs. Basically, Pavlov figured out that dogs are very good at associating the bell with the food. You ring the bell, you give them food, the dog appears. You ring the bell, you give them food, the dog appears. You ring the bell, you give them food, the dog appears. Next time you ring the bell, the dog appears without the food. And the dog keeps appearing with the bell, right? Now you associated the bell with the food. And that's true for machines also. So basically, our design was that memory controller is a reinforcement learning agent that dynamically and continuously learns and employs the best scheduling policy. So how do you do that is the key question. This is a paper that I'm probably going to assign. But basically, if you look at a reinforcement learning agent, it interacts with its environment. It observes state, it observes the action it takes, and it observes the reward it gets. And given a state, it takes the action that maximizes the reward. Right. So basically, by associating the ringing of the bell, you're trying to maximize your reward, which is the food. And you take the action of going to the person to get that reward, right? And that's true for a memory controller also. A memory controller is the scheduler over here. It's a reinforcement learning agent. It observes the state of the system, which we're going to talk about. It takes an action, schedules a command, and it gets a reward. In this case, our reward will be data bus utilization. But you could also specify different reward functions. And basically, at a given point in time, it picks the command that maximizes the long-term data bus utilization. That's the idea that we're going to explore. Or maximize the long-term reward, however you define the reward function to be over here. And it turns out this is a very good fit for memory scheduling because reinforcement learning theory, if you look at it, for this to work and converge, you need to specify the state space as a Markov decision process. And memory controller is really a Markov decision process, Markov model. And that's why it fits very well. Some other algorithm may not fit very well over here. I'm not sure about neural networks, for example. Everybody's very excited about neural networks, but it may not fit very well because that theory may not match what we have over here. So our goal was to learn to choose the actions that maximize a long-term reward value. And long-term reward value is the reward you get at time 0 times the weighted reward that you get at time 1 times the weighted reward that you get at time 2, ... That's how you actually learn to maximize a long-term reward value. This is classic reinforcement learning theory, so you can read the paper for a bit more detail. Now you can dynamically adapt the memory scheduling policy, which means that which command you choose at a given state via interaction with the system at runtime. How do you do that? You associate system states and actions, commands, with long-term reward values. Each action at a given state leads to a learned reward. Now, how do you do that? Basically, you have a state. You represent it somehow. We're going to talk about that. If you have a lot of parameters in your state, that may be a lot. So we're going to prune it. And you have the actions that you can take at this point in time when you observe the state. So this is called a state action pair. So you have many different potential actions that you can take in this state. So you form many different state action pairs. And you look at the long-term reward value that you expect to gain based on that state action pair. And you compare all of them, and you pick the action that maximizes the long-term reward value based on what you've observed in the past over time. That's the idea over here. Of course, now you need to have some memory to keep these state action pairs. You need to index some sort of table that gives you a reward, expected reward value over the future. And we use a method called Q-learning to take advantage of that. And you can read the paper in detail. Keeping the memory requirements in check is important. And in this case, we actually had a 32 kilobyte buffer in the memory controller, which is not that bad actually compared to many other machine learning techniques. Okay, so you schedule the command with the highest estimated long-term reward value in each state. And you continuously update the reward values for state action pairs based on feedback from the system. That's the idea. And the paper has more detail. So what is the state, action, and reward? This is more pictorially. You observe some state, but actually state space is very large. Action space is small. Clearly, you can only schedule some actions. There are only some number of legal actions that you can take. And reward, this is something you need to engineer, like whatever you choose to maximize. So in our case, what we wanted to maximize was the easiest thing at the time, which is data bus utilization. This is not necessarily a good thing all the time, right? If your goal is, for example, quality of service, you don't want to maximize data bus utilization, because the agent that wants the quality of service may have a very poor data bus utilization, whereas the agent that doesn't need quality of service may have very good data bus utilization. It may be streaming inherently. As a result, you will learn to prioritize this agent over this agent. Not a good idea. So you need to be very careful in terms of your reward function whenever you're designing machine learning techniques. In this case, our goal was to maximize data throughput from DRAM. We had parallel applications mostly, and we were designing for them. But there's more work that needs to be done in this area to adapt this to future other requirements in the system. So basically, our reward function was very simple. You got a +1 reward if you scheduled a read and write command, and you got a 0 reward at all other times. And the goal is to maximize long-term data bus utilization. You may get a +1 reward with the action you take immediately. Okay, you get that reward. But you may also get a 0 reward that may lead to a lot of +1 rewards in the future, right? So that equation over here that I showed you earlier takes care of that in some weighted fashion. It's not perfect, but it has some notion of long-term. State attributes, this is the hairy part, actually. This is where human designer needs to be involved very well in addition to the reward function, but this is maybe a harder part, because the state attributes are a lot. And we actually examined close to 450 or so state attributes in the system. And we pruned them out. You need to use feature selection, another machine learning method, but you need to use a lot of simulation also. Basically, you simulate the algorithm with different features, and you try to figure out which ones are the features that affect your performance the most. And this takes time, of course. And these were the features that were selected by our feature selection mechanism. Number of reads, number of writes, number of load misses in the transaction queue. You encode them with some sort of quantization in your space. And these were some of the most important features, actually, that determined which action you should take to maximize the reward. There are some also harder ones, like number of pending writes for the reference drove. This turned out to be an important feature. Sometimes you cannot easily reason about it. There's clearly some reasoning here, right? This affects how fast you can drain the write queue, for example. Number of reorder buffer heads waiting for the reference row. ROB is reorder buffer. Basically, it's a structure in the processor to enable precise exceptions. And reorder buffer head means the request was generated by an instruction that's at the head of the reorder buffer, which means that it's the oldest instruction in the processor at the time. So it's important. It's waiting for the reference drove. You'd better schedule that maybe. So that's an input to the machine learning algorithm. And request relative order in the reorder buffer. That turned out to be important also based on our feature selection mechanism. So if it's really far away from the head of the reorder buffer, basically, it's not the oldest instruction. The machine, maybe it's not as important, but if it's closer to the head of the reorder buffer, if it's one of the oldest instructions, maybe it's more important. We don't know exactly, of course, how the machine learning algorithm behaves, right? This is a black box. Yes?
So who decided these features? Like, did the machine came up with these features, or?
No. This is basically, we had a list of 450 features that we could think of in the entire system. And we ran feature selection on it, meaning that a lot of simulation to see which ones are actually the most important ones.
You thought of that. There is some inherent bias, right?
Yeah, of course. I mean, this is actually true for all machine learning mechanisms. There is an inherent bias in the reward function. There is an inherent bias in the state attributes that you select, and that's why people need to be very careful when employing machine learning in anywhere. And this is an example. Yeah, for example, we may have missed the 494th feature, right? So it's good to...
Don't rattle on that.
Say it again?
Don't rattle on that.
I'm not going to rattle on that one. That's right. That's a very good one. But that's an important point, basically. Automating feature selection is actually an ongoing research area. It's not that easy to automate, because now you need to enumerate your state space, which is possible to do, but this is where humans need to be involved somehow, and there's a bias, certainly. I mean, this is also very important, as you can see. Actions are the easiest ones over here, because you know at least which actions you can. But even there, we did some encoding. For example, read generated by a load miss, read generated by a store miss. We actually distinguished between them. That turns out to be important, because load misses turns out to be more critical. And encoding those actions separately from the reads generated by Storm has actually turned out to improve performance. Preemptive precharge. Basically, this is to close the row whenever you don't have a request to the bank. Whereas pending precharge, you have a request to the bank, and you actually need to precharge it to service that request. Preemptive is anticipating that in the future, we need to close this row. We need to precharge that bank. And no-op is another request, as you can see over here. So sometimes you may want to schedule a no-op because that's good for long-term data bus utilization. Okay. And once you have that, you leave it to the reinforcement learning algorithm. But it's not easy to design. Okay, let me give you some results. Take the results with a grain of salt because it always depends on the workloads, and we can have rattles, as Ronnie mentioned, on this. But results are actually very promising. These are actually not necessarily the most intensive applications. Basically, we gained about 19%, 20% performance improvement over the first ready, first come, first serve scheduler, which is actually a really good scheduler for most of these applications. So this is first come, first serve. This is first ready, first come, first serve. You already see that there's a huge jump by exploiting the row buffer hits. And if you actually use reinforcement learning on top of that, you get even more. And we tried to get even 5% without using reinforcement learning. We actually enumerated, we actually took these and created a lot of orderings based on these and created a lot of static schedulers that had many different orderings, and none of them actually achieved more than 5% compared to first come, first serve. So reinforcement learning is clearly doing something much better than a static ordering in the requests. And this is actually, for your reference, the performance improvement that you would get if you actually violated every single constraint except for the data bus conflicts. So it's about 70%. So that's the upper bound. It's an unrealistic upper bound that you can get because you cannot violate all of those constraints, timing constraints. Okay, so I think this is a very interesting idea, and we need to do more of this in the system design. But clearly, it has advantages and disadvantages and limitations, so it's good to cover them. Advantages, clearly, it adapts the scheduling policy dynamically to changing workload behavior to maximize a long-term target. And this dynamic is important, as I said. Static scheduling policies using the same features, we couldn't get close to even 5% with those policies. It reduces the designer's burden in finding a good scheduling policy. Designer now specifies what system variables might be useful, which is not easy, and what target to optimize, but not how to optimize it. I think how is the most difficult part over here. System variables, maybe there's a solution there as we saw here, yes?
So this is to be done on real time while the system runs during the learning process. You will get low performance probably until you
Till you initialize your tables. Yeah, that's true. I agree. I think a solution could be switching to some other policy, just like it's done with branch predictors today, right? Maybe it's basically you're talking about the warm-up time, right? During the warm-up time of the learning, maybe you use a simple scheduling policy that tries to maximize something else. But I'm not sure. But it learns very quickly, actually. According to our results, that's not necessarily an issue.
How quick? I mean, the workloads usually don't run for a lot of time.
Yeah.
Most cases, the application, even the same application tends to have different hotspots, different times, so it's not like a continuous same
Yeah.
workload running all the time.
Yeah, I mean, I cannot quantify that. It's very difficult because it's a black box, really. But we see that it actually converges relatively quickly. We can take it offline. It's not an easy answer. Basically, maybe we're losing some performance because of that initial thing, initial warm-up. Yeah, if your workload is always changing behavior, maybe other policies are not good also, right? I think that's another.
When we talk about later on quality of service and predictability, the controller acquisition, this again might become more.
Yeah, this doesn't. Yeah, this doesn't.
It does, then it's hard to predict how long it will take it to perform.
Yeah, this is not basically. This is not helping quality. The goal is not to help quality of service. There needs to be more work for quality of service over here. Yeah, we wanted to maximize data bus utilization. You're right. But I think for the warm-up, if your workload is changing behavior a lot, I don't think the other policies are going to do that well either. But quality of service is definitely. You need to do more for the quality of service. So, okay, disadvantages. Clearly, this is a black box. Actually, we don't even know. We tried to understand the policy. You can actually convert the any given point in time to a decision tree, but it's very difficult to really understand what's going on in any of these machine learning systems. And I think that visibility, that lack of observability, is a downside in any machine learning system from my perspective, but also true for the memory controller. And also designers are much less likely to implement what they cannot easily reason about, right? And here we cannot reason about things very well. Although I think there needs to be more done over here. Yeah, and the second one is actually how do you specify different reward functions that can achieve different objectives, right? Quality of service, fairness, how do you incorporate it into this? But this is, I think, a lot of potential for future work. There's a lot more to be done. And I truly think that reinforcement learning is a good approach for memory control, at least. Hardware complexity, I didn't tackle this. We actually tackled this in the paper. There's a pipeline of scheduling as to how you could generate these reward values and how you could compare them. That's in the paper. But as I said, one of the biggest costs is this table that stores the reward values for different state action pairs. And that was about 32 kilobytes in this case.
But before that, it's the goal function that you want. Forget the reward.
Yeah.
What you want to achieve, because if you say I want to achieve only the mass utilization, that by itself is a problem if you want to get the quality of service.
Yeah, exactly.
So I think that comes even before.
Yeah, I agree. That's the next one.
Learning at all. It's just,
Yeah, exactly. Yeah, I mean, specifying the reward function, specifying this even without machine learning is not easy today, actually. But with machine learning, you need to be even more creative, of course. Okay. So, but this was early work. I think there needs to be more work to build on this. And this is the paper if you're interested in looking at it. I'm not sure which ones we will assign after all of this. Yes?
This work hasn't continued since 2008?
I saw several works, actually, that built on it, that tried to incorporate quality of service. They were successful, but I'm not sure if it's really covering all of the cases of quality of service. There was a paper in HPCA in 2012 that actually looked at it. I think there needs to be more work in this area, though. That's why I'm very excited about this sort of solutions. When you have the right machine learning algorithm that actually is for the right hardware controller. And I think this is true for memory controllers, obviously, because memory controllers is kind of at the center of the world. But this is true for a lot of the other controllers as well, maybe cache controllers, non-volatile memory controllers. There's a lot more to explore over here. Okay, so maybe we should take a break again over here. We said 15 minutes? Okay, let's take 15 minutes. And then we'll continue with the rest.